Thanks. Yeah, as Stephen said, this is EU funded project with quite a large consortium, and it's looking at what happens when we spend a little bit more time exploring the dynamics and properties of the fuel that we have sloshing within aircraft tanks. So I'll just summarize that, and then the purpose really of the work that that Joe's been doing here is to look at the coupled behavior. So we're going to look at the fluid structure coupling process. Probably the most interesting thing is maybe the exchange of force and displacement between the structural model and the SPH itself. That's quite a general kind of thing. It could be used in lots and lots of different ways. It's not specific to this project. It's quite an interesting aspect of it. So I'll talk about that. Some summary of some of the results, quite a few which are pending. So Joe's working busily away, trying to get those test cases done. I'll show you the ones we've got at the moment and finish up. So brief summary to do with aeroplanes really. Most aircraft have what's known as wet wings. So the structure of the wing, it's open inside, and it's where the majority of the aircraft's fuel is stored. So you can see this is sort of the wing spar, so wing box. So there's a front spar and a rear spar, ribs around it. You're not looking at the aerodynamic wetted surface here. We're looking at the internal part, and inside that there will be many tens of tons of fuel. Sometimes also stored in the center box that joins the wings together, sometimes also stored in much smaller tanks, excuse me, elsewhere on the aircraft as well. An aeroplane's fuel fraction depends, as you might expect, quite strongly on how far it's going to fly. So if you're looking at a big aeroplane, probably at takeoff, 30 to 40% of the aircraft's weight is fuel for a long flight, obviously less for shorter flights. But, there's a lot of fuel on an aeroplane. It's probably the largest part, excluding the remainders of cargo and engines and airframe weight. It's an enormous component on long flights. So it plays a big role in the dynamics. Obviously, the inertia is a big deal. It's a lot of it there. But we're interested in this project looking at the dynamics of the behavior of that fuel, and specifically how what sort of damping characteristics it produces on the system overall. The reason for that is, well, aircraft wings are obviously subjected to many different types of loads, everything from gust to landing loads, hard landing loads, maneuver loads, and potentially misjudged maneuver loads as well. The idea is to try and make sure that the structure stays within its safe limits. And for that purpose, obviously there's a lot of work done to assess the likely loads on the aircraft, but also there are different ways of alleviating it. So you can do that aerodynamically. What we're interested in here is to see what the damping influence is. So it might not immediately be clear how a better understanding of damping leads to more fuel efficient aircraft. It obviously doesn't change the aerodynamics of the airplane particularly. What it does is it means you have a better understanding of how the structure is going to behave, and so it reduces any erroneous conservatism in the design. So you can make sure that you're not using more aluminium or more carbon fiber than strictly needed in order to meet the certification requirements of the aircraft. So if you understand your damping, you can arguably avoid that conservatism, which would otherwise give you quite a heavy or a heavier structure. So the objective of what we've been looking at as this part of the project, Sloshing Wing Dynamics load, is to perform coupled fluid structure modeling of the wing and the contained fuel. So it's obviously a problem which can be handled in a couple of ways. SPH is obviously a good one with its free surface capabilities. It can also be done, of course, with VOF, and that's also being done within the project as well. But we've been looking at the coupling part and applying a basic SPH tool to model that. So we found some quite interesting behavior in terms of effectively this is a graph of the damping that was observed during experiments. So this is a box which is it's actually mounted on a beam, and it flies up and down in the middle of the beam. And these are damping characteristics that were extracted from that time series. So the first part you can see here is labeled R1 here. We've got a region which is R2 and then R3. So not particularly exciting names, but what that labels, what those labels mean, the different type of behavior that we saw in the experiments, and also you can see on the right-hand side in this little animation. So the first region was characterized by very violent motion, kind of the washing machine type behavior. So very, very rapid motion and a lot of mixing taking place. And then the second region here, R2, this is characterized by surface waves, which are quite large, which do break and impact on the walls and the upper surface of the tank as well. And then the final region of lower damping was characterized by some smooth surface waves, which weren't breaking or reaching the ceiling of the tank or anything like that. Done a variety of tests, so these are ongoing actually. So the free release tests, which are structure coupled, which we've looked at, but also forced harmonic motion as well, which is something that is ongoing at the moment. So the aim is to have a structure coupled tool that we can use to model a 3D wing with this internal behavior. So how is it going to be done? So we're using SPH for the fluid side. Other partners in the consortium will be using VOF. The structural modeling, this is an interesting point. So aerospace tends to use NASTRAN, which stands for NASA Structural Analysis, as its default FE tool. It's a ubiquitous thing. It's got a few different software implementations out there, but that's the fundamental analysis tool that tends to get used, especially at a company like Airbus. So the coupling we're going to do here is going to use a modal model. So it's relatively straightforward structural representation. So it's linear, so we decompose into the different mode frequencies. You can see some sketches on the right-hand side. This is actually a sketch for the simulation that Joe is working on at the moment. So this is going to be replicating what was done in an experiment at Filton a little while ago. So we decompose into these different mode shapes, and because it's a linear problem, it's uncoupled. In this case, the modes are uncoupled, and we have generalized modal coordinates, which we can use to map to real XYZ space using the modal shapes. Why would we want to do this? So probably one of the most important points for this project is certainly that a lot of people are going to want to couple using the same software. So a modal analysis is something that can stand alone. So NASTRAN will digest your mass stiffness matrices and of course produce your modal representation. And you can read that into any piece of subroutine or software you want to create, and you can use those mode shapes yourself. So it means that you don't need to be directly including NASTRAN in your time loop. So this works if you're doing a linear, relatively straightforward linear analysis as we are at this point. If you want to do a fully non-linear time marching analysis with NASTRAN, you'd have to include it within your time loop, of course. But software-wise, that's quite a more substantial overhead. So everything's pre-computed, and actually all you're doing in the time step for the structural side is advancing maybe 10 or 20 different modal amplitudes, depending on how many you've chosen to use. So it's a particularly small, straightforward calculation. Obviously, it's linear, so you're looking really at reasonably small deflections, not absolutely enormous, in order for it to be completely valid. How is it implemented? So well, we've used an implicit Newmark integration scheme. So the mass stiffness damping system is rewritten in terms of modal coordinates. And what that means is that when we have a force, Fs, which is applied on the real structural system, it's converted through the transpose of the mode shapes. to generalized modal forces, if you like, and then that's applied to the differential equation in the usual way. Once you move to the modal system, the mode shapes, of course, because of the decomposition, they're all uncoupled from one another. So you're advancing effectively however many 10 or 20 simple harmonic oscillators. The implicit Newmark scheme is quite handy. It's unconditionally unstable for a linear problem, and it preserves energy exactly for linear problems, which is quite nice. So you're not going to introduce any erroneous damping, only the damping that you genuinely believe is present within that system. It's a good reason to use it. That does lead to some of the behavior that you'll see later on, where if you haven't introduced any damping, things will tend to vibrate indefinitely, of course. But it's good not to have any unwanted dissipation on the structural side. Also important is that it's unconditionally unstable for linear problems. So we don't need to worry about the time step on the structural modeling side. So it means a time step can be driven by the SPH simulation. So we don't have to resolve the problem in terms of time step differences between the two different models that we're using. That's quite useful because otherwise you'll always find that you're being driven by one particular time step. So it's quite convenient that that scheme can fit with whatever we want to couple to it. Because we could be looking at small time steps with SPH, or we could also be looking at larger time steps with other CFD tools that other partners might be using. You can include different types of damping, of course, depending on how you feel about the damping in your structure or what it looks like. That can be included as well. So one of the most interesting, perhaps important parts of this type of thing is the fact that we've got two different solvers. Now it could be SPH or it could be VOF, and we've got FE as well. And the sorts of grids that we need for each of those different methods are quite different. So there's no reason to assume that the boundary discretization, so you can see over on the right-hand side here, between the two will match. So as Joe's implemented it here, he's got these boundary SPH points, and obviously the contained volume. And then we also have the black nodes here, which represent the FE discretization. So these are FE elements. It could be whatever's chosen in the discretization, beams or whatever they may be. But those are fundamentally the locations onto which we have to transfer information. Similarly, once these black nodes are deformed according to whatever the FE software calculates, the motion has to be brought back again to the fluid boundary, so the sort of the boundary points for the SPH again. So it's important to be able to pass force from the SPH nodes across to the FE ones and displacement in the other direction. And it's immediately clear really that there's no likelihood that the discretizations are going to match. Your FE nodes are going to generally be more widely spaced than SPH would be using. And similarly, even for something like volume of fluid, those finite volume points and cells are going to be of a different size to the FE ones, which are likely to be quite big. So bridging the gap between the two is important. If you try and tie your grids together, I think you're in for a lot of trouble in terms of operating both methods potentially at, or at least one method on a grid which is not going to be optimal for it. So the exchange of information allows you the flexibility to break any links between the mesh discretizations. How does it work? So it's radial basis function interpolation. So it recovers the function through the data site, so it's interpolating. And we normally write it out as just a linear operation between the fluid nodes. So we've got the delta x, y, and z on the fluid side, which would be these black points around the outside, as a function of the delta x, y, and z on the structural nodes, which would be these Fe dark points along the inside. And you can build this single matrix that relates the positions between them via the RBF interpolation. You also need to relate the forces. So if you do a little perturbation calc, then you can show that if you want to conserve energy, you need to use a transpose of this matrix for passing forces back in the other direction. So once we know forces on the SPH boundaries, we need to pass them across to the black nodes, and we can do that using the transpose matrix. And if you want to, you can obviously link the two together. So you can link the displacements of the black nodes, the displacements of the SPH nodes around the outside, and also to the modal displacements, which are effectively the degrees of freedom you have for your structure. So there are other ways of doing this coupling between the two boundaries, but this is a particularly flexible one. It's meshless. It has the energy conservation. If you want to, you can also make sure that properties like total force and total moment are also conserved across the boundary too. So that's how we exchange the data. Now, very briefly, the SPH part of this. So I can be quite honest, and I'm going to say, I think when I first saw the slide that Joe sent, this indicates to me how quickly a supervisor loses track of a project if the students are working really hard and making lots of progress. So in summary, the SPH that's been applied is delta plus. Now, the purpose of doing that is to try and get reasonably good particle distributions, and also to not have excessive any excessive levels of numerical viscosity in the problem. So we're trying to predict the actual damping that we've got. So we don't want anything that's non-physical creeping in to interfere with that. So that's motivated choosing this particular implementation of SPH here. So it's got the particle shifting to achieve the improved positions, and also it's got this diffusive term on the density gradient. So a modification of the delta SPH, which has been used a fair bit. The integration, we actually use the same integrator, so it's a Newmark scheme again for the SPH integration. So it's implicit, so it's solved at n+1, the correct time level, so it's fully synchronized at that n+1 time level. So there's not really any scope for any spurious time shift between the two models that we're using. They should be solved at exactly the same time level. That's usually a good idea with fluid structure systems. It prevents sometimes you can predict the wrong stability if you get close to stability boundaries, if you've got any kind of time shift between two codes. To be honest, normally you can get away with not worrying about that too much if you're away from any changes in stability, but it's probably good sensible practice to try and keep it synchronized at n+1. The Newmark scheme is solved with just a straightforward functional iteration at that time step to solve it. And again, some effort that Joe's made with the boundary particles to try and reduce any spurious dissipative effects that might change the overall prediction of damping. So where's he got to? So the case that Joe's run this corresponds to this water column, and it's sitting on top of this this beam. The beam's actually modeled in the depth direction by a few elements in Nastran, and you can see you've got the fluid particles sitting on top, and then underneath we've got what represents the boundary, so the fluid boundary particles. And then the challenge for the coupling is, of course, to take forces from the SPH on these overlapping grey dots and pass them onto the FE grid, which sits underneath. And then to take the displacements of the underlying FE and pass them back onto the SPH point so that the fluid will respond. So look at what this case does. So probably before watching it, it's worth pointing out that, as I mentioned, the structural integrator, it's got good energy conservation properties and time. So if you don't, it doesn't dissipate any energy for a linear system in time, but that does mean that it, of course, vibrates for quite a long time, as you might expect. So it's a very small displacement because the beam you've got at the bottom is relatively stiff. The black dotted line here, that indicates the analytical expected deflection. It's pretty small. You can see the computed deflection is a little bit beyond that, and obviously it keeps oscillating. There's no structural dissipation there, so whatever damping is present is purely numerical on the fluid side, and fairly limited. So the sort of quasi-acoustic waves tend to rattle around for some time. However, the purpose here is really just to show that the two methods couple correctly, and the idea is then we're moving on. We've got quite close now to having the more elaborate simulations done on some of the coupled beam calcs that we want to do next. So what's that going to look like? This type of thing here. So these are the results. Unfortunately, Joe hasn't yet managed to pull out of his code. We were hoping to get them, but haven't arrived yet. So this will be the effectively two-dimensional beam. So there's a tank mounted on the end of quite a stiff steel beam. Quite large deflections though. When they ran this test at Filton, the deflections were pretty big, quite violent motion. That's going to be coupled here. The other part of the project is the experimental side. So at Bristol, other members of the group are also designing this structure here in the middle. So this is a scaled version of the full-size Wing of Tomorrow. The Wing of Tomorrow is an attempt at the next narrow-body aircraft wing structure. So it's got some of its mode shapes animated here. So that's a composite wing that's currently built or being tested at Filton. So that's quite a large external project that's running in industry. And then what we're going to do as part of SLOAD is make a scale version of this, and it's going to have a tank on it. So you can see that fitted on top. And it says here it's a 1:5 scaled model, but of course the scaling is based largely on the Froude number. So the design of this wing model is such that we match the correct Froude number between the full size and the model scale. And once we've got results on this experimental scale model, which should be quite well instrumented with cameras and such like, we'll be comparing to the fully structure coupled SPH as well. So I think that's just about it. I think that's everything we've got. Thanks very much, Stephen.
Thanks, Tom. Really interesting as always. So again, if anybody has any questions for Tom, I think the hand's already gone up in the panel, so I'll come to you in a second, Dongfang. But if anybody has any that's just viewing the webinar, again, please do put that into the Q&A, and we'll handle that. Okay, Dongfang, you had a question. Your virtual hand's gone up.
Yes. So regarding the results on slide 10, is it just the sound speed traveling between the bottom and the top of the domain? The question is whether you use a real sound speed of water or liquid in the simulation.
So this is weakly compressible that Joe's been applying. So there is the standard sort of speed of sound effect. So it's not modeling the real speed of sound of water at the moment. So it's set to effectively limit the overall density change that you might see. Yeah. What we'd like to do is run that. It's on the to-do list. Is to run that with a much lower bending stiffness, so that we can get something that's a bit more exciting, more of a curve and deflection, and then we'll get some more free surface things as well.
Mm-hmm. Yeah, thanks.
Richard has a question as well. I'll wait for my question, Richard, after you.
Hi, so how accurate does it have to be useful?
That's a good question. So I don't know, actually. I don't work in aircraft loads, so I'm not quite sure. But at the moment, there's not a great level of understanding. So there's normally an assumed level of damping that's taken in aircraft calculations. And one of the things that this would be useful for is being able to justify a level, or justifying a level which could be slightly higher sometimes, if you can be sure that that's the case. So I think it would have to be enough to prove that it was higher than had been used as the default so far. And the default so far isn't really based on any particular fluid dynamic behavior. It's in years gone by, aircraft were made of aluminium and rivets, and there's slip and things as a lot of those structures shear over each other. So there's intrinsic dissipation there. With more composite wings, there's much less. So it would be useful to know what the accurate level of fluid damping is, because then you could argue that would replace what previously existed in metal structures that were riveted, where there was a small amount of slip and things like that. I think, industry always wants, the most accurate possible method, don't they? I think probably the results that we've got so far are not too bad, but I think we'd like to close any differences between VOF and SPH and experiment as much as possible and get them within reason, within the actual measured experimental error bounds, so that we can be comfortable with it.
Yeah, I think so. It strikes me that using the simulations just to understand the functional forms you might expect would be a huge advantage, and then you could calibrate them with one or two experimental tests, right? And you'd gain so much understanding of what was going on from the simulations. Even if they're not spot on accurate, you could still use the functional forms you'd expect out of that. Yeah,
it's hard to say exactly, but my guess is at the end that it's basically, it's evidence to say for people performing the calculations on either the aircraft flies through a gust or a maneuver or hits the ground hard. It's evidence to justify what level of damping they're going to use in those calculations.
It's flutter that matters. Is that the right word? Where you get resonance in the wing that this is critical for?
Well, flutter is an interesting one because it's a sort of aerodynamic coupled one. Flutter is quite, because it's sort of it's quite dangerous. Normally the margins on flutter are quite high. So sort of, I think it's 15% away. The flutter speed has to be 15% above, where you're going to be flying at maximum speeds at any point. Which maybe as a passenger that's too close. I don't know.
It's not reassuring, is it?
It's 15% not as much as people. I don't know. Sometimes I think about 15% sounds a lot to me, but maybe if you're sitting in the aeroplane, it's not so much. So there's a fair margin on that. The thing that's quite good is to be able to, if you have like a really big gust encounter or a hard landing or a load that might have been exceeded, I don't know, in a maneuver like a turn or something. If you know the dissipation, you can work out what happened to the aircraft, and let's say, and you can argue that the loads that were seen were maybe not as great as they would have been predicted if you hadn't included that effect. So you have a better understanding of the maximum loads and also things like the amplitudes for fatigue and stuff. So probably, I don't think you'd ever be able to justify getting close to the flutter boundary using purely fuel. But if you're looking at like lots and lots of loads calculations for fatigue and things like that, then the difference that you've got can potentially make a difference to the design, I think.
Yeah.
So it's probably in the more boring part of the spectrum, actually, just where, the everyday kind of stuff that the aircraft is seeing. That's probably where this is most important, I would think.
Really interesting.